All right, so please join me in welcoming Griffin Weber and Tianxi Kai up to the podium for our next presentations.
Thank you. I'm going to do a first part on computational phenotypes, and then Tianxi will go after me and talk about some of the next future directions. So I just want to start out by emphasizing what Sean mentioned earlier about how there's things that are appropriate for large language models, and then there's a role still for more traditional computer science, engineering, machine learning. So what I'm going to talk about today is something called computed phenotypes. It's using a more traditional type of machine learning approach. It's very scalable and complementary to LLMs, and it's something that's available in I2B2 today. So I'm Griffin Weber. I'm an associate professor in Zach's Department of Biomedical Informatics and at Beth Israel Deaconess Medical Center, and a lot of others contributed to this. Some disclosures. So one question we ask is how many patients actually have a medical condition when they're coded for some condition inside of the medical chart. So physicians assign diagnoses to patients for billing purposes, even if they're just testing to determine whether or not a patient has a disease. So as a result, the electronic health record is filled with these codes that don't really reflect the patient's health. And often about half the patients with a diagnosis code really have that condition. And a problem with this is, for example, if you're looking at a clinical trial and you're trying to determine the feasibility, you'll see that there may be 1,000 patients at the institution that look like they're eligible for the study, but once you start to recruit them, half of them end up not. So it's a big problem, the accuracy and the data quality of electronic health record and having trust in the results of the resulting queries. Here's some actual numbers behind that done at Vanderbilt a number of years ago. So for patients who have a single diagnosis code for a condition, on average across different diseases, only 37% of those patients actually had the medical condition. As you require multiple codes, so more than one visit for diabetes, that goes up, but then you start losing patients and introducing some biases. It's also not consistent across different conditions. Some diseases, the diagnosis code is really good, and others, they're not so good. So this is this EHR data quality problem that we're trying to address. There's different ways you can do this. They're all under this umbrella of computed medical conditions or phenotypes. So on the left-hand side, just reiterating, there's low precision in diagnosis codes where there's a difference between the patients who have the code and the patients who really have the disease. The sort of standard way people address these are what we call rule-based phenotypes. You get a group of clinicians to come together and you come up with a set of rules. The patient has to have multiple visits of this and these medications and these laboratory values, and then they have the condition. These could be slow and expensive to build and maintain. And what we're going to be talking about in I2B2 is using AI and machine learning algorithms to automatically come up with statistical models that will find those patients. So kind of starting with the rule-based approach, we've had simple rule-based approach within I2B2 for many, many years. We just find patients who have more than one occurrence for a condition. So where you might be looking for patients with type 2 diabetes, a single code for type 2 diabetes isn't so good, but if I request patients who have at least 2 diagnosis codes for type 2 diabetes, that'll increase the precision, but it'll drop the recall and introduce different biases to it. So this is the roughest kind of way of trying to eliminate some of those false diagnosis codes in the database. You can also incorporate clinical knowledge. So I can play around with the recall and precision by looking for patients who have a code for type 2 diabetes, either or and medication like insulin or laboratory tests like A1C that are related to diabetes. Again, this requires that you have that clinical knowledge and you know the best way of combining that with your codes based on the underlying data. And if you're just presented with an I2B2 user interface and you don't know all the complexities of the EHR, you don't exactly know how to add in these additional codes to make it work correctly. You can get really complicated with this. So the FIKB website has these complex algorithms that have been developed. They'll go through various logical workflows to figure out who is the right patient. These are expensive to develop. You have to bring in the clinical experts for these. They also are hard to maintain. As new medications are introduced, you have to rebuild these models. It may not easily transfer between different institutions. So when you go to the website, there are dozens of these models out of the thousands of medical conditions that are out there, which sort of show the challenge and the scalability of doing this approach. Again, we're using machine-based phenotype. So here we're selecting a set of features automatically from the chart, assigning weights to these to come with a score or probability that the patients have the condition. You can create a tunable threshold for deciding whether or not you want the patients to be in your model out and tune the precision and recall. Now, my statistician right here, who's probably listening to me and cringing a little bit, but she'll tell you a lot more about this. My basic understanding of all this allows me to have a better threshold and automatically come up with these, and it's not relying on the expense of bringing in all those clinical experts. So this is low cost, it runs unsupervised, and it can go across millions of patients, and you can retrain these models very easily, either when you're transferring it between institutions or retraining it every month to make sure you're having the latest features and it's as accurate as possible. So the question is, we heard a lot about LLMs this morning, so why can't we just use LLMs? Why do we need this computed phenotypes? A number of reasons. First of all, there's a high cost of computation with LLMs. They're relatively cheap when you're looking at thousands of patients, but if you're trying to scale up to millions of patients and 1 billion nodes, that's where it hits these limits. The LLMs are slow relative to these computational phenotypes, which I can run on millions of patients in a matter of hours. When you get to complex eligibility criteria that are combining many different kind of phenotypes, the processing gets even more complicated for large language models. There's uncertain performance in LLMs when you're looking at low prevalence diseases, and the general issues about LLMs that we heard about all morning: values, hallucinations, ethical issues, and so on. Computed phenotypes are very predictable. It's a model that's giving me the exact same score every time I run it on the patients. So the algorithms we have in I2B2 today, there are several innovations that led up to those methods. So the first, I'm going to start back in 2010 with fee codes. So this is for something like type 2 diabetes, many different ICD-9 and ICD-10 codes in the chart that show different kind of flavors for billing purposes, but for research, they're all type 2 diabetes. So these were grouped Vanderbilt and others that grouped these codes together to say that these are a bunch of diagnosis codes relevant to type 2 diabetes, and they did this across thousands of medical conditions. And that's a starting point of rolling up the raw codes into something that's more meaningful for our research questions. And then Phenorm in 2018 had the insight that it's not just the number of times type 2 diabetes is listed in the chart, it's how many times the diagnosis is made relative to the amount of healthcare utilization the patient has. So a patient that's been to your hospital 3 times and all 3 visits are about diabetes, probably is being treated for diabetes. But if the patient has 100 visits at your hospital, only 3 of those visits ever have any kind of mention of diabetes, maybe that's not really what the patient has. So there's some context about the overall utilization they have that's really important. And then more recently, there's 2 additional algorithms. The Phenorm algorithm is just looking at the diagnosis code and utilization. Kessler is identifying additional features in the chart that are relevant to that decision. So type 2 diabetes, those patients will have these other diagnoses, laboratory tests, medications. These are all things that are co-occurring with patients that truly have diabetes and should be included in a model. Kessler algorithm doesn't give you the weights, doesn't build a model, but is looking at all the electronic health record data to show you features about patients that seem to be relevant to diabetes. And then COMAP is a very efficient method of building an actual model where you're assigning weights to those features to come up with a score on how likely a patient has that condition. And then putting it together in this pipeline, on the left we have the Kessler model. So I'm trying to build a model for type 2 diabetes, and it finds for me related conditions. It builds this knowledge graph of all the different features inside of the EHR. And then COMAP will take the 200 or so features that are related to type 2 diabetes, assign weights to those, and then you look in the patient's chart and see which of those different features the patient has, multiply it by that weight. It gives you a score, and if the score is above some threshold, Then you create a fact or an observation for them inside of I2B2, and then users can query it. In I2B2, there's this ontology list, the list of hierarchical terms on the left of the user interface, and you select and drag and drop things to build queries, and you run the query to get the number of patients who match that query. So we have to add in these phenotypes in a certain way. So under this phenotyping category, investigators have several things they can choose from. There's a phe code category, which is just the raw diagnosis code groupings from back in 2010. And there's some use case for that. If you want to have everybody who's been coded with a condition to kind of the maximum amount of recall, you can do that. Then we have a folder called probabilistic non-validated phe codes. So this is just running these algorithms as they are. They're unsupervised. It means I don't need any clinical expert to review them. I don't need a gold standard or chart review. It just looks at the data in the EHR. It tells me these are the patients it thinks it has all these different phenotypes. This is very scalable. It runs automatically. I've done this at my institution, Beth Israel, for over 1,000 different medical conditions, and it can run these in hours. But I don't really know how accurate they are. I've not looked at the notes or anything else. I'm sort of just trusting that these algorithms work. I'm not doing this completely blindly. I've seen at other institutions, they've done the chart review, and it shows that it works pretty well. But I don't really know how well they work at Beth Israel. But I can load these all in, and I can tell investigators that at other places, these worked pretty well. I don't know how well they'll work at Beth Israel, but they're probably better than the raw diagnosis codes in most situations. So here they are, but I label them, they're not validated, and they're somewhat at your own risk. Then we take a small number of medical conditions, and we actually have done some chart review with clinical nurses who can come up with a gold standard, and I actually measure how well these phenotypes work. I can assign recall and precision measures to them and put that in a third area of the ontology called probabilistic validated phenotypes. So here you're using these models, and you have confidence of what the accuracy of those actual models are. Another thing that's important in computational phenotypes, we'll talk a little bit about it tomorrow morning, we have a workshop on this, is the idea of what's the minimum amount of data that you need in order to build these models. We call this the base cohort or the loyalty cohort. So these are patients who didn't just come once to your hospital and you've never seen them again. They've had some amount of longitudinal care at your institution, and you can trust that these models have the data needed to predict whether they have a condition. So these algorithms, the Kessler and COMAP, and feeding it in and creating diagnosis codes in your I2B2 system has been available since I2B2 It's available in SQL Server and Oracle versions of I2B2. And we have a number of sites that are already using this, and we're looking for more institutions to try it out and give us feedback. This is what the chart review looked like at Beth Israel. We've run this for about 20 different diagnoses so far. The first column is looking at the positive predictive value of a single diagnosis code. And this is similar to what we've seen at MGB and at Vanderbilt and others, and that having one diagnosis code for a condition doesn't work very well. You have a lot of patients that had that one code for billing purposes and didn't get that condition. So overall, the mean positive predictive value was about 50 or so percent. As you're looking for patients with multiple instances of a code, that positive predictive value goes up. But again, you're going to be losing patients and introducing potential biases that way. With two diagnosis codes, you get up to a 0.79 precision, but again, you don't know what you've lost there. With computed phenotypes, there's a default, it's also unsupervised, a default threshold, and there we get a precision up to 0.87, and then based on the results of the gold standard manual chart review, we can do some fine tuning and finally get up to kind of our target, which is about a 90% or higher precision, giving us confidence that the patients who we're querying really are having those conditions. Or if you're looking at clinical trial recruitment, you're going to get good yield where those patients you're finding are going to have the conditions that you're looking for. However, I want to emphasize here is that, again, not all conditions are the same. In some cases, the diagnosis codes actually work really well. For prostate cancer, patients who have a single code for it at Beth Israel almost entirely have that disease. You don't need any fancy algorithms or machine learning or large language models. You just look for the code in the chart and you're done. Breast cancer, on the other hand, a single code for breast cancer, only 10% of those patients really have that condition. But if you look for 2 codes for breast cancer, then it gets up to a positive predictive value of 97%. So again, you don't need computed phenotypes, but you need some insider knowledge to know that prostate cancer is just 1 code and breast cancer is 2 codes. And you don't know that going into this. For most of the other conditions, the computed phenotypes work really, really well. But there's sort of 2 different categories. There's the ones where you can get a very high precision and the recall is good as well. And that's for the majority of them. But then there are a number of conditions where in order to get that high precision, the recall starts dropping. And you can adjust for that by tuning your threshold or combining, for example, the computed phenotypes with large language models or other methods for it. And again, the importance here is that there's thousands of different medical conditions in the chart, and no one really has characterized which are the ones that are the good codes, which are the bad codes, where do you need large language models, where are the computed phenotypes. This is a really interesting problem. We're looking at using large language models to facilitate and help with the manual chart review to do this. Sean talked about these sort of silver standard chart reviews compared to the nurses who are doing the gold standard ones. Our hope is that we can better characterize across these thousands of different medical conditions when you're going to use computed phenotypes, when do you use the diagnosis codes, and how well these work. Overall, though, as you see over here, the computed phenotypes do better than the diagnosis codes by themselves, and that idea of putting these unvalidated codes into I2B2, it allows me to tell the investigators, look, I don't know for certain across thousands of different conditions, but the majority of them work really well, better than the raw data, and it didn't cost me a lot to do that. I can run this, again, in a few hours with the algorithms that are inside of I2B2 and have these computed phenotypes generated across millions of patients. One of the nice things about these algorithms is that we're starting by having institutions running these things locally, but the algorithms also work in a federated learning model where you don't have to share patient-level data. You can share the statistical summaries and aggregate counts between institutions, and you could build models the same as if you had actually pulled them together. Why this is really important is for a couple reasons. One is these models can overfit and they can change over time. A great example that Sean told me about at MGB was they're trying to build a model for predicting patients who are going to end up in the ICU. And the model worked great. And one of the top features is, I think it was a particular mouthwash that they use in the ICU. So if you find patients who had that mouthwash, yes, they're going to have a great model for predicting which ones were in the ICU. But of course, if we use a different mouthwash at Beth Israel or they change the brand over at MGB, all of a sudden the model is going to fall apart. So you don't know that when you're looking at one hospital, but if you start collecting these knowledge graphs from multiple institutions, you would pick that out. So you're building these more robust models as new treatments and medications come about. The models will learn from that and gradually incorporate those into these algorithms. So there's a way of going from these individual institution computed phenotypes that we have now, and we hope that once we have enough I2B2 sites that are running this, we can pull the aggregate information together to build out these sort of network-wide models that will be much more accurate than the individual ones. That's where I want to stop. We're going to do a lot more on the technical details of this tomorrow at the workshop. I want to see if there's questions on this before we switch over to Tenchi. We'll be talking about some of the next generation versions of this and what else you can do with the output of these Kessler and COMAP algorithms. Yes, yeah, great.
Thank you, great talk. So the KISA is a model used for the computing of phenotype. So what is the advantage of KESER compared to LISO model and compared to a neural network-based model?
Again, Changqiu can give you a much better answer from that. But from my perspective of it, I feel it's explainability. You know, with Kessler, it's coming out with a set of features. I'm able to look at them and I go, yes, this is stuff that's related to diabetes, medications, obesity, or other things. I see the weights that come along with it. It doesn't require a lot of computing resources. I can run this right on my I2B2 database, in a few hours. I get a list of a few hundred features for thousands of different diseases. Then I can plug into COMAP, get the weights for them, and I can show people. I can draw it out. I can show the models there, the results of it. It's quick, it's explainable, it makes sense, and in most cases, it's doing better than the raw data. Of course, I can then plug it into something like neural networks or large language models and can do additional stuff there, but then you start getting into more complexity of it. So I like the simplicity of it, the ease of computation, and how well it does compared to the raw codes with just that little bit of extra added onto the base I2B2 model. You want to say some more about that?
Yeah, so similar to what Griffin had said, I think one of the key advantages is really one simplicity, is scale. It can run within few hours, it can be done. I think that's sort of the scalability, but the other thing you mentioned, for example, neural network. Most of these algorithms, such as neural network, really does need so-called labels. So you can, for example, use the ICD code as a label, but then that we call a silver standard label, basically noisy label, right? ICD code is good, but not perfect. But when you run a neural network, you actually then run into the problem of overfitting to why they are coding this. You actually want to capture why they have the disease. So in that sense, like when you have silver standard label, you don't necessarily want to train so much to understand why it's coding it. So in that sense, it definitely does not necessarily do better by using neural network. But the other aspect, as also Griffin mentioned, that by using this kind of approach, it actually naturally allow us to do the so-called collaborative learning. For COMAP, we also have a version that you can actually upload your summary statistics to our web API. You can upload it, you can run it. You can have multiple institutions uploading that. They can co-train. So it's basically naturally allow us to do the so-called collaborative learning.
Oh, you just talk about the aggregated counts and summary statistics uploaded from different sites. So are there some missing values from different sites when you aggregate?
Are there what?
The missing values of some items.
So the summary statistics, it looks kind of like a covariance matrix. And it's not even taking the lab values, it's taking how many times the lab is measured. And in the EHR, for example, if some patient does not have the ICD code, we actually treat it as just 0, not missing. So in that context, there is no missing data per se.
Another question. So can we use a large language model to build a SQL query language based on the rule-based chart workflow?
That definitely is a great question. We do have also a language model based extraction. So Sean already mentioned in the morning, for example, sometimes you want to know specific things, like when certain event happened in the EHR with the timings. So that's not exactly related to what we do here, but we're actually working with Griffin's team to see if there is a way to leverage large language model to do large-scale feature extraction. And those extracted features then can come into the model.
Thank you.
Thank you, Griffin. For your validation, you had the 1+ ICD and 2+ ICD. Have you considered validation using additional procedure or medication information?
Yeah, I mean, a point of these models is that, yes, if you had that clinical expertise, you can use these other codes to put into models. Here we're doing things that's in a fully unsupervised method. Your kind of particular questions, you could take something like type 2 diabetes and pick out something like A1C and see how closely those things are correlated. You know, again, I have to kind of pick these things out one at a time. The nurses here are so quick on this. It was almost easier just to have them go through. You don't need a lot. You need like 20 patients, to look them up, see if they have the condition, and that tells you which of those different categories the phenotypes are in. Trying to figure out what is the right medication or laboratory test for thousands of medical conditions kind of gets tricky. We're looking at using, again, large language models as a silver standard. So pull out the 20 patients, give it to a large language model and say, which one of these you think have the condition? And it doesn't matter so much if it's right or wrong. I just need to kind of get that general sense. Is the code by itself okay? Do you need the phenotypes, or these phenotypes that have poor recall to it? So that what you're mentioning is one approach, but there's some scalability.
All the manual algorithms, that's how they have been doing, right? So they're like, oh, you have diagnosis scores, great. Can I confirm using lab? Or can I confirm using medication or using those combinations? But those algorithms are expensive, like human has to curate them.
Right.
Well, thank you.
Hey, I really like the idea of federated learning rather than data comes to model, model goes to data. But I face some problems like regarding the concept drift, data drift, how you handle that. Different models on different data, different use cases domain, and we consolidate that model, we give weights to different models, and we come up with the main models. But we face a lot of problem in the concept drift, the data drift. How do you handle that?
You want
I actually will talk more about federated learning with multiple institutions in my presentation.
Okay.
This particular work is really that mainly you are relying on common ontology, although our the Kessler feature selection can select institution-specific features, and then the CoMap can run on their own data or co-train. But to really do that very effectively, when there is, let's say A1C, each of the institutions have their own code,
Right.
that needs a lot of, usually needs a lot of human intervention.
Right,
That,
right.
But we are training a shared representation learning framework to enable us to do that much more efficiently.
Okay. Another layer of abstractions there. Okay, got it.
I have two quick questions. One is practical, the other one is more technical. The practical one is that with the computational phenotype, and if I use it for clinical trials to build cohorts, and how do I reconcile this with the trial criteria, with the actual criteria? Let's see on trial.gov, they don't really specify the cohorts using this criteria. The second question is more technical, which goes to gold standard versus silver standard. And I noticed that CoMap is regressing on phenotypes. So it's doing the regression using elastic net on the phenotype, regressing out the utilities. But that still doesn't guarantee that the phenotypes that's identified through feature selection that actually is an indication of the true conditions and how that can be overcome. Yeah, thanks. Yeah.
Let me answer the second question, and Griffin can comment on the trial. So for CoMap to work, it actually takes the fee code as the silver standard.
Yeah.
And it regress against it through dropout training to really combine information from the fee code with supporting evidence, like the medication, the labs. In the end, it will have basically a combined score that integrates information from multiple sources. So in which case, it takes this basically combined score, it actually does a clustering. So it doesn't know which patient has a disease, which patient doesn't. So through the clustering, it basically tries to guess which patient have the condition. So to your question, it's basically trying to improve, denoise the fee code information, but it's not relying on the fee code as the true gold standard. So it's basically doing some additional layer of denoising by combining other information.
It comes up with a set of a more predictive, a smaller set of thin codes, and there's still no absolute
It
guarantee
comes
that
out
it's going
as
to
a
work.
predictive probability.
Yeah, right, yeah.
Yeah.
Okay. Thanks, yeah.
The other part, I may be answering a slightly different question ahead, but with clinical trials, it's usually not a single phenotype. There's multiple inclusion, exclusion criteria. And it emphasized the importance of using computed phenotypes. If I showed you the accuracy of individual raw ICD codes, but if you're requiring multiple ICD codes for different conditions, those errors can multiply. So the importance of the computed phenotypes are increasingly important the more conditions that you require for the patients to make sure that you're not multiplying your errors there. It's not just looking at the patients with the condition, it's also trying to find the comorbidities that patients have. So a rule-based model, for example, for diabetes might show you the patients who have diabetes, but then you still don't know what all the comorbidities are, but this scalable approach gives you much more accurate assessments of that. I want to stop here and let Tangqi give her presentation, make sure we have time for that, and then we can go back to
Thank you.